Hello everyone, in this video we're going to look at the experiment we did last week. So this week we looked at the fast Fourier transform library and used it in Arduino to implement fast Fourier transform. So basically we performed two tasks. The first task was to find out the pulse rate using last week's data and compare the results that are obtained from the fast Fourier transform analysis with that obtained from the DFT analysis. And the second task that we performed was to find out the respiration rate from a given set of data and plotting out the original signal by doing inverse or transform. So let's start with the first task. So here first we import the F50 library, and after that we find all the variables that we're going to use in the experiment. Here we set up the F50 object and the related variables. This F50 object is very important for the experiment. And after this we set up the Arduino board, this code, and let's now move to the main code. So basically, uh, since the F50 library works only when the size of the array is the power of 2, so basically the value the size of the array here is 75, which is not a power of 2, and now we have to take the size which is the next highest power of 2, so that is 128 in this case. So for that we have to pad zeros, and this is the code for that. So basically for the first 75 samples we are going to put the same input, and for the remaining 53 samples we are going to pad 53 zeros to the right hand side, and hence this input raw array is the array that we're going to use for a further computation. After this is a moving average filter. We pass our input raw array through this to get a filtered output, and then we perform mean removal over here. Now these two arrays are the arrays that we're going to pass to the F50 library functions. So basically VReal is the real part of the signal, and VImaginary is initially 0 because that is required for the F50 functions to work. It's given in the documentation. So here these two lines help us to compute the fast Fourier transform spectrum. So basically this line here, f50.compute vreal, vimage, n f50 underscore forward. This computes the fast Fourier transform, and the stuff is stored in vreal and vimage. This n is the sample size, and this f50 forward means the analysis equation. So we are converting it to frequency domain. And then this line f50.complex to magnitude vreal, vimage, n gives us a magnitude spectrum, and the data is stored in the vreal array. After this, we find out the first peak value and use the index of the first peak to calculate the frequency. So again, this is the same code that we did using the DFT last week. So we set two variables, kmax and kmax value equal to 0. And this kmax value will store the value of the array as it travels through the array. So since we want only the first peak value, we're going to take only the first half samples, and if vreal of phi is greater than kmax value, we're going to substitute kmax, the vreal in the kmax value, and kmax will be equal to y, that is the index at which we're getting this value. So when this for loop ends, kmax will hold the index of the frequency which is the highest, the first term. So after this, we compute the frequency which represents this first week, which is just frequency is equal to kmax into sampling frequency fs divided by n, the sample size, and then from that we compute the pulse rate, which is just 16 to frequency. So let's see what result we get in this case. So the pulse rate that we get is 70.31. So we note this fact that we're getting 70.31 pulse rate over here. Now let's check the pulse rate for the DFT code that we did last week. So this is the DFT code that I've discussed last week. It's exactly the same. I'll run it so we can compare the results. So in this case, the pulse rate that we're getting is 60, and the pulse rate that we obtained before was 70.31. And so basically you can see that the values are close to each other. And if we remember that in the past week when we ran the same code but we used the autocorrelation function, you're getting the pulse rate around 71.38, which is very close to the F50 value. Now let's move on to the second task. So this code here is exactly the same as before, but there's a slight addition that I've done over here in the computation. After the computation, So I'll just quickly go over it, what we're going to do here. So this initial code is the same as before. We are defining the variables that we're going to use. We define the Arduino F50 object over here, the required variables, and we set up the Arduino board. So basically, you're going to compute the respiration rate for the PPG signal along with respiration. So again, we have the mean set to 0. We pad the zeros as required to get the appropriate array size, and then we pass the input and pass the signal from moving average filter. We perform mean removal and we get the VReal and VImage arrays that are essential to compute the FFT using the FFT functions from the FFT library. So here again the same two lines that from the FFT library that are used to compute the FFT magnitude spectrum. So again FFT.compute will give us the FFT, and FFT.complex to magnitude will give us the magnitude spectrum and store it in the VReal array. Now here K1 and K2 denote the starting and ending points of the interval in which you have to find the required frequency. So basically these two are the variables that we are going to use to define an interval, and we have to find the peak frequency or the maximum frequency in this interval, and we're going to calculate the frequency, so calculate the frequency at this peak and use that to find out the respiration rate. So basically these values, the points 0.05 and zero point 0.5, are used to give the interval that can be found, that can be used to find out the respiration rate. So just in K1 is equal to around 0.05 into n divided by 10, where n is the sample size, and in K2 is equal to around 0.5 into n divided by 10. So again, we find out the peak value in this interval. In this case, instead of traversing half of the array, we traverse from K1 to K2. When in that interval, we find out the index of the peak value. And now using that particular index, we compute the frequency that represents that peak. And using the frequencies that we obtained, we calculate the respiration rate, which is just frequency into 60. So just we'll run this code and see the value that we get. So basically the frequency, I mean the respiration rate should be between 16 to 20 for the ideal case. So let's check what we get. So the respiration that we get is 16.11. Now let's check the same thing in case of the signal where we have only the respiration rate instead of PPG along with the respiration. So this is actually the original signal, everything else just remains the same. Now we'll run this code and see what value we get for the respiration rate. And the respiration rate value is 16.11. Now let's move on to the plots of these signals. So this code will help us plot the original signal, that is the data. So again, we have the variables that are used in our code. We have declared the F50 object and the necessary variables for it. And again, everything is just the same. We are padding the zeros, we are passing signal through moving average filter, we are doing mean removal, and we are forming the VReal and VImage arrays that are required to compute the F50. And again, the same two lines, this will give us the F50 magnitude spectrum. And now for using this F50, we are going to compute the, we are going to pass it through an inverse function. And we are going to use the synthesis equation to again convert it into time domain and get the original signal, and then we're going to plot it using this. So these two lines are used to get the original signal from the F50 spectrum. So basically the only changes that we can see here is that instead of F50 underscore forward, we have F50 underscore reverse here. So this will perform inverse F50 transform here, inverse DFT transform, sorry, and then we will be able to get the original signal, which will be again stored in the VReal array. And now using this VReal array, we'll be able to see the plot of the original signal. So just let me run this code and we can be able to see. So basically this is the case when we have PPG signal along with respiration, and after this we're going to look at the signal which represents only respiration. So this is the signal that we're getting. We can see that it looks like a PPG signal, and yeah. So let's look at the second case when we have the case where the signal contains only respirational, that is Let's look at the second case where we have only the original respiration signal. So we'll plot out the original respiration signal. Everything else is just the same as before, but we have changed the data to the one representing the original respiration signal. So let's just plot this and see how the original signal looks like. So there are certain key points in this experiment that we are going to note after seeing this plot. Let's check it out. And here we go. So basically this is the original respiration signal and we can see the plot. And this is the original plot. So basically in this experiment, there are certain points that we have to note. First of all is that we use the Arduino FFT library. That was very helpful because by using these two lines, we are able to compute the FFT spectrum and use it in our further computation. And not only that, just by changing this FFT underscore forward to FFT underscore reverse, we are able to get the reverse spectrum. And in this experiment, we first clarified, we again did the pulse check experiment and clarified the results that we obtained with the one that we did last week using GFT spectrum, and we saw that the error is not much. And after that, we found out the respiration rate using a 50 transform, and then by doing IDFT, we found out the original signal and we plotted the signal. And that's it for this video.